Okay, hello. I'm Courtney Henry, and this is my Module 3 presentation. So, the General Linear Model, GLM, is made up of two branches of multiple regression, correlation, MRC, and analysis of variance, NOVA. The equation of the model is on the screen, so y equals b naught plus b times x plus e. It is called a GLM because it generalizes to multiple, more specific models. It is model-based, and it is considered linear because it is additive. So MRC is a measure of association. The two aspects of MRC include parameter estimating and hypothesis testing. The purpose of MRC includes having more predictor specification, main effects and interactions, and rectilinear and curvilinear relationships. It is used when we want to learn more about the relationship between several independent or predictor variables and a dependent or criterion variable. It allows the researcher to ask and hopefully answer the general question, what is the best predictor of blank? This is the data I use for my hand calculation and my results for MRC. And then this is the first analysis I conducted on variables 1, 2, and 3. If you look at the bivariate plot, it violates an assumption of MRC because x and y should be linear, and it looks like there are some curvatures. First, we will look at the coefficients table. All three variables are not significant because all p-values are above 0.05. The beta values are accepted because they are between -1 and 1, and the VIF value should be less than 4, but we should still be concerned about multicollinearity. However, there's no problem with multicollinearity in this data set. x1 through 3 count for 24% of variability of y1, and they help predict it. Now looking at the model summary table, the Durbin-Watson number should be close to 2. Ours is 2.076, which is close enough, so it doesn't violate an assumption of independent residuals. So looking at our descriptive statistics, the mean is 0.1. I multiply the mean by 2 and 3. Then I looked at the output and looked at the love column. Since our mean leverage value is 0.1, we will use 0.2 and 0.3 to see if there are any influential cases within this data set. Looking back at the data I found, there are three numbers that exceed 0.2, and these will be removed, and I'll rerun the analysis. So, analysis 2. Looking at this matrix plot, there appears that there are no outliers. The outliers that needed to be deleted were deleted. Extreme outliers can have an immense impact on the results according to Cortina, so we need to proceed with caution when analyzing our data before we decide to remove any outliers. So, this violates the assumption that the variance is constant for all values of x, and the plot is heteroscedastic. Hard word to say. So, looking at the coefficients table again, if you look at the significant values of x1, 2, and 3, they are all not significant because they are all above 0.05. Now looking at coexistence in the data, no values exceed -1 or 1, so no observations need to be excluded. All of the betas are between -1 and 1, so they're accepted. And in comparing the sig values from analysis 1 and 2, they're still all above 0.05, so the conclusion is still the same, that we failed to reject the null. x1, 2, and 3 now account for 21% of variance within the data in regards of variance of y1. Before it was 24%. The VIF value should be less than 4, which they all are. And now looking at the model summary table, the Durbin-Watson number should be close to 2. Mine's 1.078, and it is not close to 2, so it violates the assumption of independent residuals. Looking at our descriptive statistics table, our mean is now 0.08. I multiply the mean by 2 again, and I got 0.16. Looking at the data set for analysis 2, there are 3 numbers of 0.16. The results are the same as the previous analysis, since we still have 3 outliers. Due to us having a smaller data set, it's not worth it to run another analysis deleting the 3 outliers above 0.16. In the residual statistics table, the mean residual error should equal 0, which it does, so it does not violate the assumption, but the mean error should equal 0. Here we're looking at if the residuals are normally distributed. They should appear normally distributed. The histogram is close enough to a bell-shaped curve, but it still is not typical. The PP plot shows our data set is normally distributed because it follows a straight line. Similar to regression, ANOVA requires linearity too. X1 and X2 are negatively correlated and it doesn't violate an assumption. So, when residuals suggest normality, it sometimes may be due to a skewed y variable. The skewness value should be between -1 and 1. Our skewness value is -0.059. Ours is moderately skewed. If it exceeds -1 and 1, then it is highly skewed and violates the assumption of normality. Since ours is moderately skewed, we're going to use the range of -1 and -0.05. Now we can confirm that our skewness data number is moderately skewed because it is greater than -0.05. Sorry, getting ahead of myself again. The kurtosis value should be between -2 and 2. Ours is -0.813, so we can conclude it is normal. It's a normal distribution based off this value. Looking at the shape, ours is close enough to the bell curve, but it is not normal because it is negatively skewed. Now, analysis of variance, or ANOVA, is a measure of differences. Is considered the analysis of variances, and it's a ratio of variances of signal to noise. ANOVA has differences compared to MRC, however, they both have focuses on understanding variance. Here is my ANOVA calculations with 2 factors and 12 observations, and some of it is color-coded for clarity and for myself more of. So when looking at sample sizes, ours is not equal in each condition. Therefore, it is an unbalanced design and violates the identical assumption. In Levine's test, we look at the sig column, and ours is 0.375, which is greater than 0.05, so we can conclude there is not a significant difference. That means we have equal variance and have not violated the assumption that the distribution of errors is normal. Now we will be assessing our F table. Our obtained value is 0.029, and the critical value is 4.26 for F1. Our obtained value is less than our critical value, so we fail to reject the null. For F2, our obtained is 2.308, and the critical value is 3.44. Again, we fail to reject the null since our obtained is less than our critical. Looking under sig values, none are significant because they are all greater than 0.05, and we fail to reject the null again. In this plot, the x-axis is predicted and y-axis is residual. This plot helps test homoscedasticity. First, we find the residual mean and look at the distance from each point to the mean. If the distance is similar, it has homoscedasticity, and if it is not similar, it has heteroscedasticity. We conclude that our plot has heteroscedasticity. MRC also assumes homoscedasticity. Dichotomous dependent variables may be a contributing factor of heteroscedasticity according to King. And that is the end of my Module 3. Thank you.